And today we're really happy to have Xiao-Gang Wen, who's professor of physics at MIT. But we heard last week about connections between US and China. And sometimes in China, there's a very big audience for a physics lecture. And here on my screen behind me, you can see a talk at the Chinese Academy of Science in the summer of 2019. And who was the speaker? Xiao-Gang Wen. So there was a very big turnout for his lecture in person, and I hope there'll be a big turnout today online to hear about symmetry as a shadow of topological order. Xiao-Gang, it's your floor.
Thank you very much. It's a really great honor to talk in this series. I have listened many good, really wonderful seminars in the series organized by Arthur. Let me just share my screen. And okay. Yeah, so today I'm going to discuss a relation between symmetry and a topological order. It's kind of a summary of recent work just appeared earlier this year. And so let's describe what is a symmetry, what is a symmetry in quantum system. So actually the quantum system we are going to study today actually have a Hilbert space which admit this tensor product decomposition, where this Vi is a small Hilbert space located on each vertex, and the tensor product of those small Hilbert space give us a big Hilbert space. Then we have a local Hamiltonian, which is sum of operator which act on each individual small Hilbert space on the neighboring Hilbert space or something like that. Okay. So that is a so-called a lattice quantum system we are going to discuss today. And sometimes those quantum systems have a symmetry. So the symmetry in general, just some kind of linear constraint on the local operators. So those operators are not only local in the sense acting on neighboring vertex, but also satisfy some additional linear constraints. And those operator with additional linear constraint is called a local symmetric operator. And then the Hamiltonian is really the sum of those sum of this local symmetric operator really give us symmetric Hamiltonian. And this local symmetric operator form an algebra of the local operator, which is essentially determine the whole quantum system. So as a example, let's consider the a lattice model where on each side we have the state on each vertex are labeled by the element of the group. So this G is a finite group. Okay, and then we have this so-called on-side symmetry, which is the symmetry transformation transform this the group index to G times H. So we have action from the right. And so this kind of symmetry transformation is called on-side because this symmetry transformation can be written as a tensor product of operator which act on each vertex. Okay, so that's what we call on-side symmetry. And this on-sideness is very important because they are so-called gaugeable or anomaly-free symmetry. And in this lecture, we'll mainly talk about this kind of symmetry. And then when you have this symmetry transformation, then the symmetric operator simply is an operator which commute with those symmetry transformation. So those are give us a symmetric operator. Then the Hamiltonian is just a sum of those symmetric operators. So so let's consider a particular symmetric Hamiltonian, and which is have this delta function of a gi times gga inverse, and this term with a negative coefficient try to make gi, gj on the neighboring side to be the same. They try to make a g all the same or constant. And then we have another operator is called a th. And this operator really act on the thi really act on this I side. We're changing this gi to h times gi. So this operator try to make gi all different. So this term prefer on each side we have a fluctuation of gi all through the group. Okay. So therefore, if b equal to 0, j is big. Okay. In this case, then this term just make all the gi the same. So we have this this is the ground state. But however, it doesn't matter which value it take. So we have a degenerate ground state labeled by the group element, and this is really called a symmetry breaking state, because although this Hamiltonian have a symmetry under group action, but each ground state is not, because under symmetry action, this G changes. Okay, and this phenomenon is called a spontaneous symmetry breaking. Okay, and certainly we know that this in this subspace of ground state, so this degenerate subspace expanded by this degenerate ground state, and there is a particular linear combination, basically sum of those states over the group. And that's a particular symmetrical ground state in this case. Okay. In the other limit where j is small, b is big, then on each side, this g would fluctuate all over this group. Okay, around this group. So there is a unique ground state that on each side is superposition of all the g. Then the tensor product of these superposition states. So there's this unique ground state, and this state is symmetric under group action. So there's no symmetry breaking in this case. Okay, and then so that is a very standard symmetry breaking model. And here I want to make a non-Abelian duality transformation to transform the previous model into another one. The new model would have a Hilbert space live on the link. So degree freedom live on the link. And then again, the degree freedom is still labeled by the group element, same group. Okay. And then the transformation is following. We transform this the operator gi, gj inverse into gij. So this group element on the link, okay, in the new model. And then the previous thi operator is transformed to this tilt operator, such that when they act on this operator again are labeled by the vertex. But when their action is that they change gij which connect to this vertex by this h. But for the link which are not connect to this vertex, they are not changed. Okay. So then we get this link Hamiltonian, which contain a term delta gij, and there's another term delta gij, gjk, gki. Okay, and in this new model, we want to take a limit where this u infinity, this u infinity is infinity in the infinite limit. So to fix this, so that to pin down this product of 3 gij around the triangle equal to 1. So actually this model is a lattice gauge theory if j equal to 0. So this condition basically is a flat connection condition imposed by this u infinity. So basically this duality really say that once we impose this flat connection condition, this new model on the link is equivalent to the older model on the side. Okay. But this equivalence is a little bit shuttle because actually the labeling between this gij on the link model and the gi on the side model is a many to one. It's not 1 to 1. Okay, it's like if you make if you make this a global symmetry transformation, they will correspond to same Gij. Okay, there's a many to one. But however, we can remove this many to one problem by restrict to the symmetric subhierarchy space for this set model. In this set model, we restrict ourselves to the symmetric subhierarchy space. And then this set model will be really equivalent to the link model. Yeah, I saw there's a question. Yeah, please unmute yourself. Just ask question. Yeah, you are free to unmute yourself. Interrupt me.
Just make sure. So usually, the symmetry of Hamiltonian, let's say the zero symmetry, is defined as some operator which is codimension one. Let's say commuting with Hamiltonian. But in the earlier slides, you are not phrasing in particular language, but these are equivalent. Is that right? Just for example,
yeah. Previous slides, when I say there's a symmetry, I mean zero symmetry. Yes.
And then you can also rephrase what you say as finding some codimension one operator commuting with a Hamiltonian, right?
No, that's codimension zero operator in the previous.
Codimension one in the space time. So codimension zero in the space, if you want.
Yeah. When I say codimension, I really mean codimension with respect to space. Yes.
Okay, fine. Yeah. So I suppose I can phrase whatever you say to just finding some operator commuting with Hamiltonian. For general Q symmetry, I just find some codimension Q plus one in the space time, but codimension Q in the space. That operator commuting with Hamiltonian. Okay, just confirm. And the last thing, make sure. So when you say non-Abelian duality, what's the emphasis of non-Abelian here? It's because the group is
non-Abelian. The group can be non-Abelian. Yeah. So that's what I mean by this. G can be non-Abelian.
Another question?
Important. Yes, please.
Yes. What's the role of the dimension? So the dimension of the space, Mn. It seems like you only.
Yeah. Right now it's not important. So far these two models can be defined on any dimension. But for easy for drawing, I just draw the two-dimensional picture.
Sure, but the claim below seems to rely on the dimensionality, and somehow you say that it's pi n, which is important, which is not obvious.
No. Here is following. There's another remark. I just mentioned that in order, actually, what we try to claim is that this side Hamiltonian and the link Hamiltonian have the same spectrum, but this identical eigenvalue requires some conditions. One condition is that the side Hamiltonian has to be within the symmetric subhierarchy space. That's the condition on the side Hamiltonian. For the link Hamiltonian, we also have a condition. We require the space to have a trivial topology, basically have a topology of a sphere. If the space have a non-trivial topology, then the link Hamiltonian have some additional features so that the eigenvalue will not be one-to-one correspondence. But if the space have a trivial topology and the side Hamiltonian will restrict to symmetric subspace, then these two Hamiltonian have an identical spectrum.
So do you require only the nth homotopy group to vanish, or all homotopy groups?
Oh,
below?
I'm sorry. Yeah, I got it wrong. This is typo. So I should say all topology. I'm sorry. Yeah, this should be pi I m n. Yeah, this is a mistake. Yeah, thank you. Yeah, you're very sharp.
Thank you.
Yeah. Okay, so this is symmetric Hamiltonian. Let me see. I think I got it wrong direction. Okay, yeah. So actually, this link Hamiltonian, this dual Hamiltonian, also have a symmetry, and this symmetry is called algebraic higher symmetry, which is the main topic of this talk. And this algebraic higher symmetry really generated in this case it's algebraic n-1 symmetry. It's generated by the Wilson loop operators, which are defined on any loop. And so this loop is really a kind of trace on a link. Okay, for any loop which is formed by those links, we can define this Wilson loop operator because we have a Gij on each link. Naturally, this is like a gauge potential so which gave us this Wilson loop operator. Okay, and so it turns out that every term in the Hamiltonian commute with this Wilson loop operator. So therefore, this dual Hamiltonian H-link have this algebraic higher symmetry. We call this algebraic higher symmetry really because the fusion or product of two Wilson loop operator where Q1, Q2 that label the representation of this matrix, which used to define Wilson loop operator. Then this transformation for WQ1 and WQ2 do not give us a WQ3, but give us some sum of a WQ3, which is really the fusion rule of representation of this group. Okay. So therefore, although this is symmetry, for this symmetry generator, we require Q to be arbitrary and this loop to be arbitrary. But those symmetry generators do not form a group. They form some kind of a fusion algebra or something. I don't know what to call it. And so that's why we call this algebraic higher symmetry. Okay. If the group is abelian, then there's a Q1, Q2 give us unique Q3. And so this fusion will be group-like. And this is called a higher symmetry. So in this case, this symmetry, this higher symmetry will describe by this higher group, and will be called a higher symmetry introduced in this paper. Okay, so this is a very simple model which give you an example of algebraic higher symmetry. Yes, please.
The fusion rule n here is not necessary to be positive integer or zero.
It's a positive integer or zero. It's a positive integer. It's a non-negative integer in this case.
It can be proven.
It's a fusion rule of the group. You know, representation theory. It's Q1, Q2, Q3 gets a label representation of the group. And yeah, and this product, although as an operator, they seems this can be any coefficient, but when you really using this RQ is representation, then they are really integers.
Is this an assumption? Or is
can
this
be proven.
Is
it
it
can
this
be proven.
proven?
It can be
Thanks.
proven. Yes. Okay, so just like the ordinary zero symmetry, we have this phenomenon for spontaneous symmetry breaking, which we discussed a moment ago. This algebraic higher symmetry also have a spontaneous symmetry breaking. Okay, so let me just describe this a little bit. So in a limit where like b equal to 0, j is big, we always assume this u is infinity. Okay. Then we have a unique ground state. When j equals to 0, the b term would sorry, this b equal to 0, j is large. So j term would make all gij equal to 1. Okay. So we have this a unique ground state because of this j term. Okay. And then in another limit where b is large, j is small, then this term make superpositions. And so actually this term tries to pick the flat connection because this is flat connection, but this term just say the superposition of all flat connection gave us a ground states. But however, if M is a sphere, then there's only unique flat connection configuration with this different superposition, and there's unique ground state. But if M is have a non-trivial topology, then the flat connection may have a non-trivial holonomy across this along this non-contractile loop. So then that gives us several degenerate ground states if M have a non-trivial topology, just like a gate theory. So I'm really describing a gate theory here. And but however, this degeneracy was regarded as a spontaneous symmetry breaking of this algebraic higher symmetry, because the symmetry transformation on this algebraic on this degenerate ground state is not proportional to identity. So basically, to define this spontaneous symmetry breaking for the algebraic higher symmetry, we require two things. One is that we have a degenerate ground state on some space-time, some space manifold with a certain maybe with certain non-trivial topology. And then the sum symmetry transformation are not proportional to identity on this in this ground state subspace. And so indeed, in this case, this degenerate ground state satisfies this condition. So we say they have a spontaneous breaking of this algebraic higher symmetry, this Wilson loop symmetry. But in this case, there's unique ground state, so there's no symmetry breaking in this case. Okay. And so we can see that there's some kind of duality here. These two models, set model and the link model, have some duality because they are dual and they have same phase diagram. But somehow the zero symmetry breaking state correspond to the symmetric states for this algebraic higher symmetry. They are dual symmetry, and the symmetric states is a symmetry breaking state for the dual symmetry. So there's a switch of a symmetric and symmetry breaking. Okay, and the funny thing is, let's assume actually I'm not sure. Let's assume as we change in J and B, there's these two phases are connected by the single critical point. If not, we have to make some fine tuning. And if they are connected by the single critical point, we can see that this critical point is a part of this symmetric phase of the zero symmetry, and also part of a symmetric phase of a higher symmetry, this algebraic higher symmetry, actually touching that. And so we can say that this critical point have a both symmetry, at this critical point. So therefore, the critical point have a both symmetry G and the dual algebraic higher symmetry. And this is actually main of motivation for this study, because we always want to looking for the emerging symmetry at the critical point as much as possible, so that we hope we can use also emerging symmetry to characterize this critical point. The critical point is really a very tough problem, and how to study critical point is very important. And here is the idea that maybe the critical point have very big emerging symmetry, which have both zero symmetry and algebraic higher symmetry. So we try to use this kind of a property to characterize critical point. But this is not the main topic of this this talk. But this is one of the main motivation to study this kind of symmetry and dual symmetry, because they may provide a more complete description of a critical point and the gapless states. So because they are so important, so we put these two symmetry together, call them a categorical symmetry. So this categorical symmetry is really a combination of symmetry and the dual symmetry. And so we make a notation like that, this string notation. And this categorical symmetry is the main topic of this lecture. So later I will explain why we have this very strange notation.
Excuse me.
Okay, please.
Can I ask a question?
Yes.
So what would the categorical symmetry be if the global symmetry G, original symmetry, is anomalous?
Okay, if they are anomalous, this description is no longer valid. And anomalous symmetry, categorical symmetry can describe anomalous symmetry, but in a different way, not in this, not using this this picture. Yeah, this picture only apply for anomaly free theory, anomaly free symmetry. Anomalous symmetry is a anomalous symmetry is a little bit tricky. I mean, this is not convenient way to look at the anomalous symmetry in this way, but using categorical symmetry, there's a way to do so.
Yeah, but in some sense, the categorical symmetry there implies you actually have a mixed anomaly between the G and the G tilde higher symmetry, right?
Yes. So that's one way to say. Actually, I think if G is abelian, you can say that this categorical symmetry is a symmetry of a G and a G tilde, and they have this they have a mixed anomaly. I'm not sure this picture works if G is non-abelian, because at the end it turns out to me categorical symmetry is a much better concept. That's for me. Okay. Anomalous symmetry turns out to be inconvenient. It's a little bit artificial. So in our new work, we try to de-emphasize anomalous symmetry and replace everything by categorical symmetry, which include anomalies. This phenomenal anomaly included here. But I think this is a better way to look at anomaly. And
that's something.
For your question that when G and G tilt, when G is abelian, you can use anomalous symmetry to understand categorical symmetry. When G is non-abelian, I'm not so sure. I haven't really looked into this, but I feel probably not. Yeah. Go ahead.
May I ask you a question?
Yes.
Do you need to have you assumed that the critical point is a first order phase transition?
No, the continuous. So here I assume continuous transition. This critical point is a continuous transition connecting to these two both phases. This may not be achieved by this model. This model may not have that property. If not, we have to fine tune this model to reach this critical point, continuous transition.
Okay, thank you.
Okay. So actually, the spontaneous symmetry breaking for the higher symmetry or for algebraic higher symmetry have some strange properties. We know that for the zero symmetry, the spontaneous symmetry breaking is robust against any local symmetry preserving perturbation. Okay, but they are not robust against the local perturbation which break the symmetry. Okay, so therefore the ground state degeneracy associated with the spontaneous symmetry breaking is a property of the symmetry for the zero symmetry. But however, for the higher symmetry or for the algebraic higher symmetry, it turns out that this degenerate ground state for some manifold, okay, is actually robust against any local perturbation which can break the symmetry explicitly. Okay, this is very strange. So, but certainly, this ground state degeneracy is robust against the symmetry preserving perturbation, but also robust against symmetry breaking perturbation. So in some sense, to associate with the ground state degeneracy with a symmetry seems a little bit strange. So it's not property of algebraic higher symmetry. So this is a little bit kind of strange things. Okay. So actually, because this ground state degeneracy is robust against any perturbation, so actually it's a property of topological order. Okay. And so far, we only consider this finite discrete group. When you have a continuous group, we also have a U1 symmetry. It turns out that the spontaneous symmetry breaking of U1 symmetry gave rise to gapless gauge boson, like a Gaussian boson. Okay, but here again we have something similar, that this gaplessness is robust against any local perturbation which can break explicitly this U1 symmetry. And so looks like it's kind of strange to think about this spontaneous symmetry breaking as a phenomena of a symmetry or higher symmetry in this case. But if you insist to think that way, then here is the way to do so. That is actually because although we have perturbation which can break the higher symmetry explicitly in a lattice, but at the low energy somehow there's an emergence of the higher symmetry. So that's really the point. For some topological order, we have emergence of the algebraic higher symmetry, and then this emergence of emergent higher symmetry is spontaneously broken, which in turn provide this ground state degeneracy for those topological order. So therefore, we can understand the topological order in terms of emergence of algebraic higher symmetry, and in addition, a spontaneous breaking of this emergent higher symmetry. Then we can understand topological order this way. But not every topological order can be understood that way. Only some topological order can be understood that way. Also, this whenever we have a spontaneous breaking of a higher symmetry, that's also imply there's some topological order. So there's a close connection between topological order and a spontaneous breaking of a higher symmetry. So this is just a remark. Okay. So we have seen that this side Hamiltonian and the link Hamiltonian are are due to each other, or essentially we call the dual equivalent. Okay, because under certain condition, these two Hamiltonian can have the same eigenspectrum, identical eigenspectrum. And but here I want to say that this dual equivalence can be more general. Actually, you have a so-called dual equivalence of a symmetry. So in the following sense, if you have for the arbitrary set Hamiltonian with a zero symmetry, G, then we can find a dual Hamiltonian with algebraic n-1 symmetry, so that these two have the same spectrum under certain condition. And reverse also true. For arbitrary this Hamiltonian with algebraic n-1 symmetry, then we can find a set Hamiltonian with a zero symmetry, so that these two Hamiltonian have same spectrum. So in the sense that this zero symmetry G and this algebraic n-1 symmetry G tilde actually is the same symmetry. Sorry, they are really the same symmetry, because they are equivalent constraint that select the same class of Hamiltonian. But by same class, I really means there's a one-to-one correspondence of the set Hamiltonian and the link Hamiltonian. So there's so they just select a set, the G symmetry select a class of set Hamiltonian which have a one-to-one correspondence with the link Hamiltonian, which is selected by this dual symmetry. So they basically select same set Hamiltonian or equivalent set Hamiltonian. So in that sense, these two symmetries are equivalent. So that's so we have the sense of a equivalent symmetry. So this is one of the main topic of this lecture. But here, using this example, we just introduce this concept of equivalent symmetry. So this zero symmetry and the algebraic n-1 symmetry can be equivalent. And then here's another remark. Okay, so how to view these two symmetry? Okay, so actually the symmetry, the zero symmetry G already imply a dual symmetry. In the following sense, we can say that a Hamiltonian with a symmetry G also have a dual symmetry, this n-1 symmetry. And then because they have both symmetry, so we can also say the Hamiltonian also have this this categorical symmetry. Similarly, if you have a Hamiltonian with a dual algebraic higher symmetry, then we also say that the same Hamiltonian also have this zero symmetry, and also have the same algebraic categorical symmetry. So here I emphasize, here we are talking about the Hamiltonian. We say Hamiltonian have those symmetry. But however, the ground state are different. In the ground state, somehow it must spontaneously break part of a categorical symmetry, like in this case. In this part, the G symmetry, the zero symmetry is a spontaneous breaking. And in this part, the n-1 symmetry is a spontaneous breaking. And so this categorical symmetry, because this anomaly or because something, because they have some so-called mutual statistic between them. And so therefore this gapped ground state must spontaneously break part of a categorical symmetry, either G or G tilde or some combination. Okay, so this is a very interesting property of this categorical symmetry. And also you can see that's a phenomenon of anomaly. Okay, but I think this categorical symmetry is a little bit more general than anomaly. Have this same thing. And then there's the ground states with a full categorical symmetry, which at this critical point must be gapless. Okay, so if you want to have a full categorical symmetry, then the ground state must be gapless. So the point I try to make here that Hamiltonian always have a full categorical symmetry, but the ground states either break first part or break second part. For the ground state to have a respect to full symmetry, it must be gapless. So this is another way to look at how the categorical symmetry can connect to the gapless system. Okay, so we have a yes, please.
Is there a way in which the structure of this categorical symmetry constrains the nature of the gapless phase, like the type of phase transition, for example?
Yes, and this is really the maybe kind of the holy grail of this approach. We wish this is true. So basically, knowing categorical symmetry, we'll know the gapless states.
Mhm.
But here I want to say, but this is not main topic of this talk. But this gapless states, I should say, is a gapless states with a linear dispersion relation, not like a Fermi liquid gapless states. That is too complicated. There's some so-called simple gapless states with a linear dispersion relation. It's like a CFT, and then we wish this emergent. Here I have to emergent. The categorical symmetry we talk about here is a lattice categorical symmetry. But however, the gapless system may even have a bigger categorical symmetry, which you call emergent maximal categorical symmetry. And we wish this emergent maximum categorical symmetry fully characterize gapless states. And this is a wish actually mainly proposed in this paper. And but we check this in 1+1 dimension, that seems working. But in higher dimension, we don't know. Yeah.
Excuse me.
Yeah.
Thank you.
In higher dimension, let's say even it's possible in 2+1D or above, there could be a possibility to have a phase that preserving the full categorical symmetry, but having TQ of T or topological order, in a sense.
Yes.
So not necessarily gapless to preserve the categorical symmetry, right?
No, so
you can have just
so okay, the statement is following. If the lattice model have this categorical symmetry, which is preserved in the ground state, then the ground state must be gapless.
Well,
so this do not contradict of what you just said. You can certainly stack with topological order with these gapless states. You can get some additional categorical symmetry, which is a spontaneously breaking part of it. Yeah.
But let me phrase this again. So the categorical symmetry here, actually there's a mixed anomaly, a mutual mixed anomaly between the G and the G tilde higher algebraic symmetry.
Maybe only for G abelian. For non-abelian, okay. I'm not so sure.
That's fine. So let's focus on that case. There's a way in certain anomaly or in certain symmetry, a certain choice of this G is possible to have a full symmetry preserving but a gap phase with TQ of T or topological order, right?
Yeah, that's a spontaneous break some of the categorical symmetry.
Okay, I understand.
So the topological order is a spontaneous breaking of some dual symmetry or some symmetry.
Oh, thank you, thanks.
That is that situation. Okay.
I'm sorry, could I ask if could you give is there an example of, like, when you mentioned some of their combination, is there a combination that's not G or G tilde that you can break?
Oh, if G have some subgroup, if G like a Z2 times Z3, then there's some combination of you break a Z3 and a Z2 tilt, you know, something like this combination.
I see. Okay.
If G has a product of some smaller group, then you can imagine those different combinations.
Thank you.
So as a symmetry, in the symmetry we know they have a charged particle. So actually, for the zero symmetry, the charged particle just repetition. Yeah, please, Jovan.
Actually, Xiao-Gang, I think what I say is still correct. And what you maybe didn't get what I say. I think it's still possible to even preserve both G and G tilde, the full categorical symmetry, by cancelled by long range entanglement with anomaly. In certain case, in that phase, there still could be additional higher symmetry spontaneous broken, but that's not the G tilde here.
Yeah.
Anomalous topological order cancel also possibly cancel mixed anomaly. It's like people call this confinement or confinement with symmetry breaking. As confinement in like a maybe for QFT series. So that's possible also.
So I do not rule out the gapless states may have a spontaneous breaking of some categorical symmetry. You know.
Yeah, I think
I do not rule out that possibility.
I mean another thing, but I can follow up later. You can keep going. Thank you.
Yeah. So we know that the zero symmetry have a charge particle, which is simply representation of this symmetry group. Okay, and similarly, this algebraic higher symmetry also have a charged particle or charged object. Okay, so here let's consider a situation where this b equal to 0 and j is not 0. In this case, the ground state is a symmetric ground state, so we can talk about the charged particle. In a symmetry breaking state, it's hard to talk about the charge excitation. Okay, so this ground state simply gets a Gij to 1 on every link. It's very trivial ground states. Okay, on this ground state, we can create a so-called charge object by changing Gij from 1 to h along this loop in the dual lattice. Okay, so then this loop object is actually we call the charge object of this algebraic n-1 symmetry. Okay. And this loop object actually corresponds to this charge anti-charge pair for zero symmetry, because in 0 dimension S0, this 0-dimensional circle is just 2 points. So these 2 points correspond to charge anti-charge pair. So therefore, this charge object is a totally charge neutral. Okay. And to get a charged object, we need to consider part of the loop, or basically like a part of S0, which is 1 point. Okay, so part of the loop actually is open loop. So charged object is changing Gij from 1 to h along a open string, not loop, open string. Okay, so using gauge theory language, we can say that at the end of the string we have a gauge flux, which is more convenient. And then this Wilson line operator, or this higher symmetry operator, going around this this end of a string, will be measure the charge. So so this is a charge and the charged object. Okay. And so we know that the zero symmetry are described by group. The higher symmetry is described by higher group. So here the questions are, what kind of mathematics describe algebraic higher symmetry? Okay, and here we want to say that we can using those charged excitation to describe a symmetry. Like for zero symmetry, the charged excitation are just a representation of the symmetry group, and for the one symmetry, the charged object will be loops, or the open string for charged object. So therefore, we can see that for higher symmetry, we have this extended object as a charged excitation. Okay, so therefore, the higher symmetry are described by this charged object, which can be point-like, string-like, or membrane-like, and the collection of all those kind of excitation really forming a so-called higher fusion category, and that is really the main message. That maybe we can use a higher fusion category to describe this algebraic higher symmetry. And this is the mathematics to describe algebraic higher symmetry. Yeah, please.
Excuse me. Actually, the convention people use for
maybe since we have so many slides left and only 15 minutes,
okay.
we could
Right.
let the speaker.
Yeah, I think the convention was not quite a match with the usual people call the higher symmetry Q symmetry. Anyway, the dimensionality problem. All right. Thanks.
Yeah, I'm talking about the space. Yeah, I think match up anyway. So so we have the so let's give some example. You know, what is this using higher fusion category to describe symmetry? What is that? So we consider the Ising model, where the Hamiltonian just a sum of a poly Z operator, and so the excitation in such a simple Ising model actually is something can be trapped. For example, we can modify the Hamiltonian on particular site to add the trap delta H, like 2 times this Z I0, or some kind of combination of Z I0 and this X I0. Okay, some trap. And then there's the new Hamiltonian would have a gapped ground state also. And this gapped ground state of new Hamiltonian is called excitation. And we have excitation types. That is, if 2 trapped excitation can deform into each other without closing the gap, we say they are equivalent. So in this case, like a one spin flip and two spin flip will be equivalent. So actually, in this case, if there's no symmetry, there's only one type of excitation. And this type of excitation actually can be continually deformed to ground states, so which we call the trivial type. Okay. But however, if you have a Z2 symmetry generated by this poly Z operator, then this trap Hamiltonian must be symmetric operator. So in that case, we find that a single spin flip and a double spin flip can no longer deform into each other using this symmetric trap because this second trap is not allowed. And but however, double spin flip can deform into ground states. So double spin flip is trivial, single spin flip is non-trivial. So actually we have two types of excitation in this case. The type trivial one is trivial one, and the type E, which is a Z2 charge or representation for Z2 group. Okay, the type E. Okay, and so this one and E form this fusion have a fusion rules. They have fusion rule, and in particular, it's E fused to one is really representing this mode 2 conservation of this E particle, and this mode 2 conservation imply this Z2 symmetry. Okay. I want to say that here we are doing 2 plus 1 dimensional theory. So actually, this 2 plus 1 dimensional theory, this point like a particle generate a fusion 2 category, okay, which are written as this 2 rep Z2, okay. And this fusion 2 category, we have an object. The object actually is a string-like excitation, okay. So we have a trivial string, which we don't talk about that. And a non-trivial string. This non-trivial string is a condensation of this E particle. We know that the E particle has this mode 2 conservation. So their condensation may give rise to a spontaneous Z2 symmetry breaking. So this ES string is a Z2 spontaneous symmetry breaking string. It's a face living in 1 dimension. Okay. So and so this is non-trivial string, but it's descendant. It's not elementary. It's a descendant coming from this E particle. Okay. And so the string excitation or object in this fusion 2 category is this string excitation, and the point-like excitation is just an E and this 1 and E we talked about before, which is like a 1 morphism. And we also have 2 morphism. This is symmetric, local symmetric operator really connecting the point-like excitation to another point-like excitation is a 2 morphism, which is in physics called instant time in space-time, which are really 2 morphisms, which is topomorphism. So we have a 2 layer of morphism, so that's why we call this a fusion 2 category. Okay, so the similar thing also works in 1 plus 1 dimension. In that case, the point-like excitation would behave like a object, because when you lower 1 dimension, we have a fusion 1 category. The object would correspond to this Z2 charge we talk about, and there's no string. And the morphism would be the local operator would be 1 morphism. So that's why we have, in 1 plus dimension we have this a fusion 1 category. Okay. And in the fusion 1 category, we have a famous Tanaka duality. That is the fusion of a charge object gave us a fusion category. This encodes all the information of a symmetry group. So therefore, the fusion of a representative fusion of symmetry group encode the group itself. Okay. So therefore, we can use in the fusion category to fully describe a symmetry. And here we try to say that a conjecture or guess, a wish. The same thing is true for the in higher dimension. That is this fusion N category N rep G fully encode this information of group, and so it's really describe a 0 symmetry. Okay, and so basically this represents a categorical way to describe a symmetry using fusion to describe symmetry. That's a fusion rule corresponds to conservation law, which correspond to symmetry. For example, I just mentioned that this zero symmetry G are described as n-rep G. This fusion n category. And similarly, this dual symmetry G tilde n minus 1 is also correspond to fusion n category, which is n vector G. It's a graded vector space. The fusion category formed by graded vector space. Okay. So so we have this we just described that the fusion higher category really describe symmetry. But actually, the more general use of fusion higher category is to use them to describe excitations in a topological order. Okay. For example, let's consider an example that's a topological order, a Z2 topological order in 2 + 1 dimension, which basically is a Z2 gate theory with a charge or the Topological. You know, usually when people say Z2 gate theory, sometimes have a charge, sometimes don't have a charge. But here, when I say Z2 gate theory, I always include their charge. Okay, so this Z2 topological order have excitation described by fusion 2 category, which have this notation. We denote as like this. Basically, this notation means Z2 gate theory with a charge. The 2 morphism is a topomorphism, which is just a local operator with no symmetry, just any local operator. The 1 morphism are this point-like excitation or domain walls. These elementary excitation, point-like excitation, are these familiar, this trivial one, EM and the fermion F. Okay, and the fusion rule of E gave rise to this Z2E symmetry, and we have fusion rule of M give us Z2M symmetry. We also have Z2F symmetry is a fusion rule of fermions. The object would be like a string-like excitation in this fusion 2 category, which is the E condensation is a Z2E symmetry breaking, or Z2M spontaneous symmetry breaking, or Z2F spontaneous symmetry breaking. You know, in 1 dimension, the Fermi statistics don't mean anything. So even fermion can condense in 1 dimension. Okay, but this Z2F symmetry breaking, spontaneous symmetry breaking, actually is another way to say the P-wave topological superconductor. This Marana chain first studied by the Kitev. Okay, so those are just example of this Z2 fusion. This is fusion 2 category describing topological order. So using this example, we can already see we have some problem. So we have a fusion 2 category describing 2 + 1 topological with no symmetry. We also have a fusion 2 category, this 2 rep Z2, describing 2 + 1D product states, i.e. trivial topological order with Z2 symmetry. So therefore, if you want to use a fusion 2 category to describe a symmetry, there's an issue which one describe topological order, which one describe symmetry. So we have to really have some special fusion category, fusion higher category, to use them to describe symmetry. And so one thing to distinguish the two is following. For the fusion higher category, which describe topological order with no symmetry, then it has this property that it cannot be mapped to this 2 vec. Okay, this is a trivial, it's like a trivial fusion 2 category describing the excitation in a trivial topological order of product states. However, this 2 rep have a particular property that it can be mapped. Here, mapped, I really mean the functor. You know, I'm using map because of maybe some physicists are not familiar with the functor. And so let me try to explain what I mean by mapped into this 2 vec. And so let's consider this S3 symmetry. This is symmetrical group S3. So their fusion 2 category will be 2 rep S3. It has 3 type of particles. That is a 1 morphism, and which is a trivial representation, 1-dimensional representation, which is A, and a 2-dimensional representation, which is denoted as a B. Okay. But however, this 2 vec as a trivial state on the trivial state have a 1 type of a particle, just a trivial excitation, trivial particle like excitation. Okay. So this map or the functor from 2 rep S3 and 2 vec at this one morphism level. So I'm thinking about the map between particles, particle-to-particle mapping as one morphism level. Really map this the trivial representation into the trivial particle in trivial states. Wrap this one-dimensional representation into the trivial particle. But they map a two-dimensional representation of S3 into the direct sum of two one-dimensional representation. It's really like this accidental degeneracy because it's B is a two-dimensional representation. It have a 2-degree freedom in it. It corresponds to two accidental degeneracy of a trivial type. Okay. So this is this kind of like an embedding or the mapping. So every particle in this rep S3 can be mapped into the particle in the trivial fusion category. But you could have this kind of accidental degeneracy. And at the morphism, at two morphism level is the operator. So this map is the operator to operator map. That's a map the local operator into the symmetric local operator into local operator. And this map almost like embedded. So this is like an injective map. Okay. And so therefore, however, for this non-trivial topological order, it contains fermions or contain particle with non-trivial mutual statistics. Therefore, for this kind of non-trivial fusion category describing non-trivial topological order, it cannot be mapped into this 2-vec because 2-vec have only bosons, have no mutual statistics. So this mapping is not allowed. So therefore, existence of this mapping is a property for the algebraic higher symmetry. Okay, so this really using this intuition, we see that this algebraic higher symmetry, we know that this zero symmetry is classified by that group. Higher symmetry is classified by higher group. Then the algebraic higher symmetry is classified by so-called local fusion N category. Basically means it's a fusion N category which admit this so-called a map from R to this N-vec. And but this map is called a top faithful. The top faithful means that at the top level is an injective map from local symmetric operator to local operator. At the other level, maybe we don't have other conditions, but we are not totally sure. So this is a proposal which may be true, or maybe at the other level we might need some additional condition. But so far, this is our proposal. And so physically, this map really means a symmetry breaking. So we just ignore the symmetry. When you have a fusion category describing a symmetric states, you can ignore the symmetry, view this as a category describing excitation in a system without symmetry. You can at least view that way. So existence of this map means that the symmetry is breakable. So if the R describe a symmetry, the symmetry is breakable, we should reduce to this N-vec. But somehow, if the fusion category have a structure which is not breakable, so it's not symmetry. So that means that fusion category would contain a topological order. So how much time do I have?
You've really used up your hour. So if you could finish in the next 5 minutes or so.
Okay, yeah. So let me try to finish in 5 minutes. Okay. Okay. So there's another way there's a second way to look at this. That is the fusion 2 category. Again, we have these two fusion 2 category. One describes topological order without symmetry, another describes topological with symmetry. What their difference? One way to say the difference is that the first one is a non-degenerate. Okay. The second one is a degenerate. The degenerate or non-degenerate really means remote detectability. The non-degenerate means remotely detectable. That means every non-trivial elementary excitation, I emphasize, every non-trivial elementary excitation can be remotely detected by at least one other excitation via remote operation. The remote operation, just like a braiding, like these two particles, one particle braid another one. If you see a face, that means you can detect the other one by remote operation. Okay. So if the fusion category, if it's non-degenerate, there's a proposal that a conjecture that then this fusion category can be realized by a lattice model in the same dimension without symmetry. Okay, that means we can have a lattice model in the same dimension without symmetry, whose excitation happen to describe by this fusion 2 category. Okay, and there are another way to say this. That is, the lattice model in the same dimension can be viewed as a boundary of a trivial topological order in one higher dimension without symmetry. Okay, so therefore, this non-degenerate means that it have a trivial bulk. It's realizable without symmetry, or it's a boundary of a trivial bulk. That's the meaning of a non-degenerate. Then the degenerate means that it's not realizable in the same dimension with the symmetry, without symmetry, and it have a non-trivial bulk. It's a boundary of a non-trivial bulk topological order, and this is really suggestive. That means it is a bulk topological order means symmetry. So therefore, whether a fusion category describes symmetry or not describing symmetry, we just look at its bulk. If it's a boundary of a trivial bulk, it have no symmetry. If it's a boundary of a non-trivial bulk, it have a symmetry. So therefore, the bulk topological order is a symmetry. So this is really describing this, maybe the main message of this talk. The symmetry is a shadow of a topological order in one higher dimension. Okay, so to be more concrete, or maybe a little more rigorous, is that we have this holographic principle of the topological order. Okay, so we really have 2 conjectures. One is any fusion category can be viewed as a boundary of some topological order in one higher dimension. Okay, and so there's a relation. So any fusion category can be viewed as a boundary of a topological order in one higher dimension. And there's another conjecture is that the relation between these two are kind of a magnitude 1. So that is this boundary fusion category uniquely determine the bulk topological order. Okay, so the given bulk topological order, we may have many boundary fusion category. But however, given a boundary fusion category, there's only one bulk topological order which corresponds to that. Okay, so there's a map from the fusion category at the boundary to the bulk topological order, and this map is called this E1, this E1 center. When n equal to 1 for one category, for one fusion 1 category, this is well-known Greenfield center. So this is generalization with Greenfield center to higher dimension. Okay, so therefore, this map really computing the bulk topological order from the fusion n category. Okay, and this really computation of the symmetry. So a fusion higher category may describe excitation in topological order with or without symmetry. Okay, how do we tell whether we have a symmetry or not? Then we just compute their center, and their center tell us whether they have symmetry or not. So actually, their center is a symmetry. Actually, the center is what we call the categorical symmetry we introduced before. Okay, the center is not directly symmetry, but the center is precisely the categorical symmetry we mentioned before. Okay, so maybe just maybe one slide using this slides to say that. So like this Z2, maybe this last slide. Using this Z2 symmetry, we see that the Z2 symmetry, the boundary is this 2-rep Z2. We have an E and an E. Okay, their bulk is a Z2 gate theory. It have this E, this Z2 charge, and the Z2 flux, this S. Okay, so the boundary is 2 plus dimension. The bulk is 3 plus 1 dimension. Okay, so one boundary of a bulk is that we have a string condensation. Then we only have a 1 and an E. So then we get this Z2 symmetry. This 2-rep Z2 describes Z2 symmetry. And we can also have a E condensation to get a different boundary. Now here, this boundary only have S. And this S actually is have this correspond to this Z2 1 higher symmetry, this 1 symmetry. Okay. And so together you can see that, But when you look at the bulk have a both E fusion rule and S fusion rule. So we have a mode 2 conservation of E and S2 mode 2 conservation of S. So we have a both symmetry. So these two symmetries together as a bulk, we have a categorical symmetry like this. So the bulk is a categorical symmetry, and the boundary is this different way of categorical symmetry breaking, and which give rise to different symmetry. Okay, so this is really just a way to look at a symmetry and using this holographic point of view, and so let me just end with this slide. So this is this cylinder like a categorical symmetry. The different projection is like a different symmetry. So that's what I mean by symmetry is a shadow of a topological order in one higher dimension. Thank you very much.
Well, thank you very much, Xiao-Gang. That was a really beautiful picture that you drew for us, and it fit nicely into the picture language seminar.
Yeah.
So I wonder, do you have condensed matter examples which illustrate some of these symmetries and symmetry breaking?
So yes, actually in 1+1 dimension, we can use in this picture and try to view the critical point CFT. Certainly, we don't need that because 1+1 dimensional CFT is well studied and we know them. But however, using this new way to look at it maybe is give us some hint on how should we view CFT in higher dimension. And also, there's an issue about whether this algebraic higher symmetry can exist in condensed matter or not. And the answer is yes. As I mentioned, the topological order always have an emergent categorical symmetry at have emergent algebraic higher symmetry at the low energy. So therefore, when you study the topological order and the phase transition of topological order to some other neighboring phase, and then there's an emergent higher symmetry or algebraic higher symmetry which control this critical point. So this, I would say, this may be the most important application of this this kind of formalism.
So I see there are many experts on symmetry here. So there, I'm sure, a great deal of questions and discussion. Anybody who wants to ask a question or contribute should unmute themselves.
I would like to ask a question.
Yes.
Xiao-Gang, in your summary, when you talk about these categorical symmetries and so on, how the existence of the emergent symmetry is related to the gapless excitations?
Yeah. Okay. Yeah, this is something I did not talk about. But let's say let's assume we have a topological order. It have all kinds of excitation, you know. But we could have a limit where some subset of excitation have very low energy, other excitation have very high energy. Okay. Then there's a subset of a low energy excitation. They can fuse and break, and they form a fusion N category. This low energy excitation form a low energy fusion N category, and that's it. This low energy fusion N category is not non-degenerate, and it have this so-called algebraic higher symmetry, or more generally categorical symmetry. Then any phase transition induced by those low energy excitation, like this low energy fusion category, will be controlled by its center, by its categorical symmetry. And so this is a way to have a emergent higher symmetry or categorical symmetry, and how to use them to understand a phase transition near a critical point. So it's a very, very general. And this also point of view to look at the duality, because in this point of view, the symmetry charge and the topological excitation are treated at the equal footing. So we could have a mixed symmetry and low energy topological excitation. They're combined to give us a low energy emergent categorical symmetry, and which control the phase transition with the symmetry and with some topological excitation. Okay, so this is really just a view. This everything kind of viewed in the same footing, and certainly this anomalous symmetry also is included in this kind of point of view. And so one don't need to introduce anomaly anymore. Just using this categorical symmetry as a boundary topology order, you can uniformly study all those phenomena at equal footing.
Okay, then what you have said is related to the details of the Hamiltonian, because we know that some Hamiltonian may have symmetry breaking.
Yes.
So which changes the nature of the spectrum. I mean,
yes.
gaplessness or not.
Yes.
Or,
yeah. Yeah.
Okay.
So this is a very good question, very important question, and so this also subtlety. So when I say categorical symmetry or emergent categorical symmetry, I really means the symmetry for the Hamiltonian. Okay. The ground state of that Hamiltonian may break categorical symmetry. Probably have to, may break it. So when I say this low energy excitation topological order have emergent categorical symmetry, I really means that there's a class of Hamiltonian with this categorical symmetry, which can simulate the low energy dynamics of those low energy excitation with some arbitrary interaction. Basically, it means that when I say low energy excitation, I assume they may have some arbitrary interaction. But those arbitrary interactions are simulated by Hamiltonian with arbitrary interaction, provide that they have this emergent categorical higher symmetry. So therefore, this the all different interaction between low energy excitation are encoded in the all different term in the Hamiltonian with this categorical symmetry. So that is a correspondence. So really the mapping from class of Hamiltonian describing low energy excitation and the class of Hamiltonian with the categorical symmetry. And we claim that these two classes of Hamiltonian have a one-to-one correspondence. So therefore, you can use a Hamiltonian with a categorical symmetry to fully simulate low energy topological excitation and their interaction. So that is the meaning of using emergence of categorical symmetry and using categorical symmetry to study phase transition. So it is in this sense.
Okay, very good. But I have another question. Do you have some example realizing this, especially in 3+1 dimensions?
Realizing what?
In 3+1 dimensions,
yeah.
Realize what you have said, which is a very general statement.
Oh yes. So let's consider a 3+1 dimensional gauge theory, Z2 gauge theory. Okay.
Okay.
And it have this Z2 chart, which is point-like, and Z2 flux, which is a string-like. And we can consider confinement transition induced by the string condensation. That's a string condensation is a confinement transition.
Okay.
Currently, the confinement transition is not first order. It's first order, not continuous. But let's imagine we can fine-tune the interaction to have a critical point of a string condensation. Then now here in this string condensation confinement transition, we can assume a charge always have a very high energy or maybe infinite energy, ignore them. And
okay.
So therefore this confinement transition have this emergent higher symmetry. I think this is Z2-1 symmetry. All this we can solve this Z2-1 symmetry also imply this categorical symmetry, which is a Z2-1, Z2-1. These are both Z2-1. So there, so this categorical symmetry are described by a topological order in 4 polar dimension, which is Z2 rank 2 tensor gauge theory.
Okay.
Can I ask a related question? Do you have in your framework a way to distinguish between a pure ground state and a mixed ground state?
No, here we only do quantum theory, so we don't have a mix in the density matrix sense. That's a kind of finite temperature behavior. And so we have a ground state, we have a ground state subspace. And certainly you can create a density matrix of that, but we in this we don't discuss that. Yeah. Or maybe you have different meaning of a mixed ground state. Do you mean density matrix mixing or superposition mixing?
No, I mean density matrix.
Oh yeah, we don't talk about that. But that is a different direction, which is really trying to study the final temperature effect of those kind of systems.
No, you can have a mixed state, but also a super selection rules.
Yes, and you're totally right. The things that you can see, for example, in the symmetry breaking, of a zero symmetry, we restrict ourselves to the so-called symmetric sub-Hilbert space, and which is we restrict ourselves to this superposition of all different ground state, like O up plus O down. And but this is a superposition mixing, and they are not a density matrix mixing. And yeah, in our discussion, we don't include that. Yeah, it's a little bit different topic. Yeah.
Are there other questions?
Can I ask a quick question?
Yeah.
I was wondering how a two group fits in this sort of framework. I guess it's not a categorical symmetry, is it? Two
group, it is. It is a higher symmetry. Okay, so there are too many symmetries here. So there's a symmetry, zero symmetry, or higher symmetry, and algebraic higher symmetry. Okay, so that's from symmetry point of view. And then the bulk of those symmetry are categorical symmetry. So categorical symmetry means the bulk. Okay, and so this is maybe a better way to look at it. So therefore, the two group symmetry is a higher two symmetry, and we can view this as a shadow of a topological order in one higher dimension. So that means it is the boundary of gauge theory in one dimension. So that's how a two group symmetry fit into this this framework.
Mm-hmm. So I guess the categorical symmetry corresponds to the two group gauge theory, not
yes,
the two group
in one higher
itself.
dimension. Yes, it's a actually categorical symmetry. Better to view them as a living in one higher dimension. It's do not even live in the same dimension. It's living in one higher dimension. So really, this picture is so this cylinder is a categorical symmetry, and the square and the circle are symmetry and a dual symmetry.
Mm. I guess, do you know what is dual to a two group in this case?
Yeah, and this is something is in this picture. So when you have a fusion category to describe algebraic higher symmetry, how to find is a dual symmetry. The dual symmetry is that we first find the bulk. Then this bulk have another boundary, which gave rise to correspond to another symmetry, which have same bulk. Okay, and if the stacking of this give us a trivial topological order, then this R and R tilde will be a dual symmetry. So this is a way to understand the dual symmetry. Okay, and so if two categorical symmetry, higher symmetry, have the same bulk, we say they are dual equivalent. And the symmetry and the dual symmetry are always dual equivalent, but they also have additional condition that this stacking give us a trivial states. Okay, and so there's a lot of things like the similar stacking. Actually, RR stacking gave us a gauging. The gauging of a categorical, gauging of a higher algebraic symmetry is a stacking R and R, and this gives us a gauged theory. Yeah. So actually, this using this algebraic, this categorical point of view, we can study all these property of the gauge of categorical symmetry. Yes. Sorry, algebraic higher symmetry.
Thank you.